because for any x, you can only have one value of y. Follow? So for any x's here, you can only have one value of y because you have a flat line. So that means y and x, they are not related at all. Okay, so that is the case. So this p-value, therefore, is trying to test whether this line, this is from your experimental data, this one, this flat line, whether this line is different from this line. In other words, whether the slope of this line generated from your data is any different from this flat line, which is with a slope that is 0, equal to 0. Okay, so this is the idea of this p-value. Now, how about this dotted line here, dotted line here? This is the confidence limit. So you are saying that this line, you are quite confident that 90% of the chance that this line, this black line, will be the true line that will represent your population of the relationship between these two sets of variables. Okay? So let me show you another example. Hopefully, it will become more clear. If you look at this example, what do you get? P is less than 0.01. So that means this line that you have generated from your set of data is significantly different from a flat line. Okay? Yet, if you look at this other parameter that I said we should pay attention to, is the R square. This R square is very small, only 0.01. What is the meaning? This means that only 1% of the variability within your data can be explained by this line. So again, although from p-value ANOVA test, you know that the slope of this line is significant, yet your R square is very small. It means that you have a lot of data, but only 1% of this data can be explained by this straight line. So again, this means that this line is meaningless because this cannot explain a lot of the information in the data. So these two have to be reasonably at a reasonably level, like in here. So you have again some points. In this case, you look at the R square, it's 0.6956. So roughly you can say that the line you generated, the so-called regression line, can explain 90%, can explain 70% or 69.5% of the variation within your data. Okay, so that is the idea of the R square. And in here, the ANOVA, value is also less than 0.05. So in this example, in this third example, this line then has a meaning. It is then describing the relationship between your x and your y. Okay, in the previous two cases, if we go back, you have significant line, slope being significant, only a very small amount of the variation within the data can be explained by the line. So the line is meaningless. Okay? The other one, R square also actually is quite small in this case, but I want to emphasize in this case, the p-value is not is greater than 0.05. So that means the line is not different from a flat line. Okay, so again, this line will not explain a significant relationship between your x and your y. Okay, so I hope you get this clear. Huh? So very important to consider both the R square and also the p-value. Okay, like in the last case. Huh? Both the R square and the p-value is less than 0.05. That That means your line, the line could be negative or positive, could be increasing or decreasing. Okay, so p-value is less than 0.05. That means your line is significantly different from a flat line. And yet, and then also your R square is quite big. There's no rule of how big is R square should be, how big the R square should be. But roughly, if you say 0.5, 50% of your data can be explained by the line that's reasonably good already. Okay, so you can have, in this case, R squared is 0.6956. So you can roughly say 70% of the variation within your data can already be explained by your line. Okay, and that is the idea of the so-called regression analysis, is to find whether you can define a relationship between your x and y by a straight line. Now remember, x is the cause and y is the effect. So there's always a cause-effect relationship between x and y in a regression analysis. Okay? Okay. Let me move on. Look at the last one, which is called a correlation. Correlation simply means that two things happen to be behaving in the same way, or you're trying to find out whether how they behave. Do they behave in the same way, or do they behave in the opposite way, or maybe there's no relation. Okay? So this is a measure of the so-called covariation. There is no assumption of cause and effect. Very, very important difference between regression and correlation. In correlation, no assumption of cause and effect. In correlation. In regression, you always have an assumption of cause being the x value and the y value being the effect. Okay? So correlation analysis is expressed in terms of this so-called correlation coefficient R. And this ranges from 1 to -1. When R equals to 1, that means if y increases, x will always increase. So you have a positive correlation. On the other hand, if you have R equals to -1, that means for y, every time y increases, x will decrease. So you have always an opposite response. So in this case, you have a negative correlation. If R is 0, there's no relation. Okay, x may increase, y may increase. They do not behave in any way. Okay? In this case, you also need to test for the significance between the relationship. I will show you an example. If you have x, any x values, and you have some y values, you have two sets of data. You want to compare whether for every x, when an increase in x, whether you have also an increase in y. Okay, so in this case, what do you get? You get a very good correlation. Okay. Now, remember the graphical representation is quite similar to your regression. You also have x and y, and you can have a line like that, points or data on the graph. Okay. But remember, if this is a regression, you are saying that x is independent and y is dependent on x. But if this is a correlation, then you are not saying anything about whether which one is the cause and which one is the effect. So that in regression, you cannot interchange between x and y. But in correlation, you can. You get the same result. Okay, if you interchange the y with x, you will still get the same line. Okay, but you cannot get that in regression. So in this case, for every y increases, x will increase, so you can say x increases, y will also increase. So R will be equal to 1. Okay. So how about if R is equal to 0? You will have a Finally, I will show you just a actual data. Here you have many parameters. These are heavy metal. Okay, in some seaweed algae. Okay, now the question is, do they follow the same trend? Do they have the same trend? Okay, if this one, for example, this one, if you look at this one, what is this? Okay, this is copper. If this one, this is over time, huh? If this increase, will this also increase? This other one, let's say, nickel. Okay? So in this case, if you just compare between the copper and nickel, you will find out that, okay, the pattern of these two are quite similar. Okay, they will increase, but they are not 100% similar because here you have increase, but this decrease. Okay, you have increase in this one, but this one decrease. And yet, in most cases, you have an increase. This one will also increase. Okay, so the general pattern is similar, so that you will not get a R value that is exactly equal to 1, because there is some slight difference in the pattern. So that you need to use a statistical test to find out whether the correlation is significant. So in this case, p-value is less than 0.05. Excuse me, 0.05. Therefore, the correlation is significant. Okay, so far, okay, so that is the last topic that I'm going to introduce. Okay, so if we summarize all the key points we have taken so far on statistical analysis, we have descriptive statistics, we talk about populations, we talk about samples, and you have sample mean versus population mean, sample variance versus sample population variance, etc. So always you're trying to say whether your sample mean can represent your population mean. Okay? And whether your sample variance can represent your population variance. And then I introduced some inferential statistics. Okay? Comparing between samples, whether they are the same, the two means are the same. And I mentioned that if you have only two sets of samples, you use t-test. If you have more than two sets, you use ANOVA. Or if you have more than two factors. Okay? On the other hand, I also described the difference between regression, where you have cause-effect relationship being defined, and the correlation simply covariation,